Hello, you're welcome to day 2 of 50 days of tutelage, and we're doing physics today. We'll be treating the topic measurement and unit. So let's define measurement first. I'm sure that measurement is not a strange thing to anybody here. You have heard of measurement before. Measurement of, especially if you want to sew a clothes, you go and take your measurement in the tailor's whatever. Anyways, measurement is actually the process of assigning numerical values and units to a certain reading. So in science generally, we like to take measurement of things. However, this measurement usually involve three things. Although we are only conversant and familiar with two major parts of these three things, but as a scientist, a good measurement should always involve three things. Don't forget, it is the act of assigning numerical values to a particular reading. But a good measurement must have three components. So let M represent measurement. A good measurement must have a numerical value. A numerical value. A good measurement must have a unit. That is, you must know the unit with which you are using to take the measurement. And a good measurement must also have what we call the error bound. The error bound. So as you can see, I know most of us, we are familiar with the first two, the numerical value and the unit. If you take a measurement of a length now, you can get something like 22.5 centimeters. So what you notice is that 22.5 is the numerical value and centimeters is the unit of this particular thing. Now, so what do we do? What is now error bound? The purpose of error bound is such that we want to give a form of accuracy to our measurement, because there can be so many errors based on the instrument that we have used, or the instrument due to human factor or error due to human factor itself. So there's a lot of things that can give rise to error in our measurement. So therefore, we always leave a form of error bound to show that, okay, what I've measured, it's safe within this particular range of values. Although I have gotten 22.5 centimeters, but the better way to write it will be, let's say, 22.5 plus or minus 0.05 centimeters. Now, you could write it this way, or 0.15 centimeters. So what you have done is that you're telling us that the 22.5 that you have measured, you can, maybe when you do your own measurement, you can get something a little bit above 22.5 or a little bit below 22.5. And when a measurement have all these three elements, that is the numerical value, let me call that NV, it has the error bound, let me call that EB, and it has the unit, let me call that U. Then you say you have an accurate measurement. An accurate what? Measurement. So that is what measurement is in science generally. Now let's quickly go into some quantities that we have in physics. In physics, we have two major types of quantities. Now, I'm not speaking in terms of advanced nature of quantities now, but we have what we call the fundamental quantities. We have the fundamental quantities and we have the derived quantities. So we have fundamental quantities and derived quantities. By the way, you know that you need to get your note right now. So if you don't have your note already, quickly get it so that you can take note of what we are teaching. Now, so fundamental quantities, derived quantities. Some of these things are just English language. What does it mean for something to be fundamental? Fundamental means that it is kind of necessary. It is not brought about. It is the one that will bring about something else. So when we say something is fundamental, it is essential. It is actually the bedrock, the backbone of whatever it is that we're going to be doing. So if there are quantities in physics, then there are some quantities that they just exist on their own. Nothing gave birth to them, but they will be the reason why we are able to get other quantities as well. And in fact, all those other quantities that we are going to be getting are called derived quantities. So we have basically 7 fundamental quantities, and I'm going to tell you everything about them in this video. So the first one is mass. We're going to be talking about mass. Mass is a fundamental quantity, meaning it is the amount of matter that an object contains. So for every object to exist, in fact, what we say is that matter is anything that has mass and can occupy space. So the fact that you have mass The fact that you exist, you are a matter, and therefore you have mass. So mass is the first fundamental quantity, and the SI unit of mass is kilogram. The second fundamental quantity I will talk about is length. So as long as it exists, as long as you can see it, it means that it is in a way long. By the way, the concept of length is not is generic. So because some of you think that, oh, there's something called length, breadth, width, height, and all of those things. All of these things are length together. Length is just the measurement of how long something is. So let's say you have so in the concept of mathematics, if you have a triangle and let's say the length of this guy is 4, the breadth is 3, but I can also say that I have another rectangle and I can say the length of this guy is 6 and the breadth is 4. So you can see that 4, which was length earlier, is now the breadth. So when we say length here, we're talking about the generic measurement of how long something is. Breadth, width just come from comparison so that we know, oh, they are measuring how deep something is. You are measuring a shorter length compared to something else. So the SI unit of length is meter. The next one is time. Time is another fundamental quantity which is measured in seconds. It is measured in seconds. So time is definitely a fundamental quantity because it cannot be created. It is only used and combined with other fundamental quantities to produce derived quantities. The next one now, so the remaining four, these are ones that may not be very, very common. So temperature, you must have heard of temperature before. Temperature is also a fundamental quantity and it is measured in Kelvin. Temperature is simply the measure of how hot or how cold an object is. And you know that if matter exists, definitely there will be a particular way it is. It's either it is hot or cold or lukewarm. It will definitely have a kind of way it feels whenever you touch it, even though touching a body does not accurately measure its temperature. I'll talk about the device that we use to measure this thing later on in this video. So temperature is also a fundamental quantity. It is measured in Kelvin. The next one is electric current. Electric current, and that is measured in ampere. Electric current. Electric current is simply the rate of flow of charge on through a body or through a system. The rate of flow of charge through a system. As you are as an individual, you are made up of charges. And we have the two types of charges, positive and negative charges. What makes you neutral is because the amount of positive charge in you is the same as the amount of negative charge in you. So these charges, they neutralize each other out, and therefore you have neutral charges. But whenever something has more positive charge than negative charge, that thing will become positively charged. If you have more negative charge than positive charge, that thing will become negatively charged. So, but the flow of this charge through a body is called electric current. And note, when we say a body in physics, we don't necessarily mean physical body. We're talking about object, a matter. So that's that about electric current. So let's go to the next one. The next fundamental quantity, that would be amount of substance. This one is measured in moles. This one, we'll discuss a lot about it in our chemistry class. Amount of substance, which is what? Mole. Is more of a chemistry concept than a physics concept. So we've talked about mass, length. So let's see how many do we have here. We also have luminous intensity 2, 3, 4, 5, 6. And the last one, we have the luminous intensity. Luminous intensity. So this has to do with light, and this is measured in candela. So the unit of luminous intensity is candela. So what happened is that these are the fundamental quantities in physics. Like I've defined earlier, they just exist. You can't really trace that, oh, is there a quantity before them? So they are not brought about by other form of quantity. For instance, if I want to talk about the first derived quantity now, which is, let's say, volume. Now, if you begin to break volume down, you see that volume is coming from area, but area itself is coming from length. So you can always break volume down and find a previous quantity that brought about. So before you can have volume, you must have area. Before you can have area, you must have length. So volume is a derived quantity. Volume, a derived quantity. Area, derived quantity. Now, when you get to length, the question is that where are you going again? There's no place to go again. So length is fundamental. So you can't find a before for length. So you can only find after for length. So, but for derived quantities, there is always a before. So, example of time as well. You can't find a before time. Like, it's just time. So that is why it is fundamental. So I've given you one example of derived quantity. There's also acceleration, there's velocity, and so many more that you will learn in the course of these 50 days of tutelage. By the way, if you have not subscribed to the channel yet, this is the right opportunity to do so. And also, if you're learning something in this whole thing, make sure you share with your colleagues. Share with as many classmates of yours as possible. Let them know and let them know about this because there will be so many things to learn here. So let's continue the class. Now, derived quantities, you can look for as many as possible as well. Don't forget to take your notes. You will write tests periodically as well. So now we have talked about the fundamental quantities. We have talked about the derived quantities. The next thing we want to talk about dimensions. Dimensions. Now, what is dimension? Dimension is basically what we use to describe more like a uniform way of describing quantities. So, for instance, there are quantities that share the same, let's say, unit. For example, you have length, like I was explaining earlier, you have length, you have breadth, you have width, you have height, and so on and so forth, like that. You have all of these things. But there's a particular thing we use to represent them, which is known as dimension. So if I give you dimension, you know that, oh, this dimension represents any sort of measurement like this. And it gets complicated whenever you are actually trying to do for derived quantities. For instance, if I say, what is the dimension of acceleration? You should be able to find it. But it is quite easy as well. How do we find dimension for most quantities that we'll be coming across? There's a very, very simple way to do that. The simple way is to know the SI unit. And for SI unit, all these guys are the SI unit for the fundamental quantities. Don't forget, derived quantities are gotten from fundamental quantities. So therefore, this unit will always be present in them. Now, when you know the SI unit, for instance, what is the SI unit for acceleration? That is meters per second squared. So if you're wondering that, oh, I don't know anything about acceleration yet. Anyways, we will talk about it in the course of these 50 days of tutelage. Also, most of these units, you will just get used to them as time goes on. Now, what about force? The unit of force is Newton. But if you want to break it down into SI units, so take note of it now, it is kilogram meters per second squared. Now, we have many other ones as well. We have work done, which is joules. If you break it down into SI unit, it is kilogram meter squared per second squared. Now, so let me limit it to this now. The moment you know the SI unit of any quantity, then the dimension is easy because all you have to know is that for mass, the unit is kilogram, SI unit is kilogram, and what represents it in dimension is capital M. For length, the unit is in meters, and the dimension that represents it is capital L. You can see L for length, M for mass. And for time, the unit is seconds, so and what represents it is capital T. So all you have to do is to watch out for this guy. So let's find the dimension for acceleration now. Acceleration is meter per second squared. Meter corresponds to capital L, and seconds corresponds to what? Capital T. What's the power of S here? -2. So the dimension for acceleration is LT raised to -2. Let's do for this as well. Kilogram corresponds to capital M, so we have M, and then we have meters, which is L, then we have T raised to -2. Then we have for work done now, that will be kilogram, which is what? M as well. This time around, L is going to be to the power of 2, and seconds, which correspond to capital T, is going to be to the power of -2. And this is the dimension. So this is the key to knowing dimension of any quantity in physics. All you need to do is to always find the the SI unit that corresponds to that. And so for today, the last thing we're talking about under this particular for day 2 is I'm giving you some devices, and what we use to measure them. Sorry, some quantities and what the devices we use to measure them. For instance, now mass. If you want to determine the mass of an object, we use beam balance. You can take note of all these things. For the mass of an object, we use what? Beam balance. For length, distance, generally, we use meter rule. There are other devices as well, like the vernier calipers, the micrometer, screw gauge, measuring tape, and so on like that. But meter rule is the common one. Vernier caliper and micrometer, screw gauge, they can only measure very short length, and they are much more accurate than the meter rule, but they can only measure short length. So we don't necessarily use them all the time like that. So that's for length. I've said something about mass, the beam balance. And then for time, we use stopwatch to measure time. Stopwatch or clock for general timekeeping. That is what we use clock for. But stopwatch is what we use in the lab to measure time whenever we're doing any experiment. For temperature, we use thermometer. Thermometer is a device used for measuring temperature. For electric current, we use the ammeter. We use ammeter to measure electric current. Now, for voltage, we use voltmeter. For resistance, we use ohmmeter. For pressure, if it is atmospheric pressure, we use barometer. Now, if it is gas pressure, we use manometer. manometer, manometer. So we have so many devices like that. For light luminous intensity, we use what we call a lux meter or light meter. Lux meter or a light meter, and so many of them like that. So in the course of this 50 days of tutelage, as we are measuring some other quantities, I'll be giving you what we use to measure them as well. And so that's basically what we have for today's class. Don't forget to like, comment, and subscribe. It goes a long way to help support these 50 days of tutelage. If you enjoy what you are receiving here, share with your friends in your classroom as well. It is very, very important. And if you have not registered, make sure you register. And that's it for day 2. Signing out. I'll see you tomorrow.